Alright, welcome to our 8th video of Unit 3 and our final video of Unit 3. Yay! This is called Intermolecular Forces. This concept is actually very prevalent throughout, well, especially AP Chemistry. Not too hard to get, just make sure you pay attention, as always. So, different properties such as bonding strength, pressure, and especially melting or boiling points really depend on the actual strength of the forces between the molecules. So the stronger the forces, the higher those properties. The forces are called intermolecular forces, and these determine, like I said, many properties of substances. For example, salt. Have you ever, melted salt? Like, ever? You probably dissolve salt in water. You've used salt in cooking all the time, but do you ever think about how you never really find liquid salt? That's because of these intermolecular forces. It has a very strong one. Ice, however, you melt ice all the time. You drink melted ice all the time. It's water. So the difference is not just in the chemicals, but how they're bonded together. Certain bonds require less energy to melt, or break actually, and thus they can melt easier. So those are intermolecular forces. The strongest forces exist within ionic compounds, and they're simply we call them ionic bonds. Now these compounds, like this cube-looking thing, form due to the attraction of cations to anions, and vice versa. They make very, very, very strong attractions, which makes really, really high melting points, which is why you won't find liquid salt. Here's what happens though. You see this? That's a cation. I'm pretty sure you knew that. Cation, cation. Those are all cations. These are anions. What happens is you have a cation gets attracted to these anions, which get attracted to the cations, which get attracted to the anions. And you have all these kind of interweaving, it's called lattice structure, and everyone's being attracted to everyone around them, and it's a really crazy strong bond. That is the strongest ionic force. Now, most of our time, however, will not be spent on ionic compounds. The other types of forces that we are going to spend our time deal with what we call the polarity of the molecule. Now, before continuing, the following must be true for a molecule to be nonpolar. Now, I know that's a little bit counterintuitive because I said polar and nonpolar. We've talked about polar before with the unequal poling. It's just easier to think of a molecule as being nonpolar. It's an easier way to make a checklist, if you will. And if it fails any of these checklists, then it's polar. First off, all nonmetals have to be in the compound, as in every compound is nonmetal. If it's a metal, then we're dealing with ionic bonds, not polar bonds. I'm going to try some real quick. I've got a lightsaber option. We're going to see. Try it again. I have a sound. That's okay, not doing that anymore. I'll figure out how to turn that sound off at some point. Well, we tried. Oh well. So to be nonpolar, we need all nonmetals, and there has to be no lone pairs of electrons on the central atom. Kind of like molecular shades, but you can't have any lone pairs. Okay? If that's true, then you need every atom bonded to the central atom to be the same element. So, if you have something where it's all nonmetals, no lone pairs on the central, and every atom's the same element, it is nonpolar. If any of these are false, then it is polar. So let's look at up here. We have oxygen is the central atom. Yes, everything is a nonmetal. Yes, hydrogen, the only elements bonded to oxygen are the same element. But there are lone pairs. So up here, this is polar. Because it failed to be nonpolar. Hope that makes sense. Okay, up here, same elements. They're all nonmetals, but we have lone pairs. So this is polar. All nonmetals, same element. There's no lone pairs. This is nonpolar. Yay. There you go. Alright, let's have a little bit more practice. H2O. We got H, O, H. Okay. Are they all nonmetals? Yes. Are they the same element? Yes. Are there any lone pairs? Yes. Which means this is polar because there needs to be no lone pairs to be nonpolar. Now, I'm going to have you, I'd like you to pause real quick. Try the next three. Okay? Now, I'll tell you, NaCl is kind of a trick question, but try these. Don't just sit here and listen to me. Try them yourself, and I'll wait a bit. All right, I'm done waiting, so I'm going to move on. NaCl is our next one. And here's the interesting thing. We have to have all nonmetals. NaCl is not a nonmetal, which means it's a metal, which means this is ionic, so our answer is neither. Polar and nonpolar doesn't work for ionic bonds. Polar and nonpolar implies an unequal sharing. There is no sharing in ionic bonds, it's just taken. So, there you go. Our next one is NH3. Okay, these are all the same element, but we have lone pairs, which means polar. And CH4. All the same element, no lone pairs, nonpolar. I just realized that these are both examples I did beforehand. I didn't quite mean to, but seriously, it's the same method. So, there you go. That's how you find if molecules are polar, nonpolar, or neither. So, if a molecule is nonpolar, now we can start labeling intermolecular forces. Nonpolar means London dispersion forces. Now, in truth, these actually exist in every compound, and they actually get stronger due to how many electrons we have in the substance. In nonpolar molecules, however, these are pretty much the strongest one. They're weak, but it's the strongest one in nonpolar molecules, so that's the main force. Now, what actually happens is basically, as your electrons are kind of swirling around the atom, at some point we say there exists enough electrons on one side to act like a temporary polar molecule. And that is attracted to others who are being temporary polar. And you have this kind of vague attraction that sometimes occurs. It's not very common, that's why it's not very strong, but it does happen. You have enough electrons on one side, they kind of are pulled in one way, and you end up having this kind of temporary attraction. We call those London dispersion forces. Now, most of the time, a molecule is polar. So if it's polar, and it has both an H and at least one of N, O, or F, we have hydrogen bonding. Again, meaning H and N, O, or F. So H and N is okay. H and O, H and F, sure. Just O, no. Just F, no. Just H, no. So that's hydrogen bonding. If not, it has dipole-dipole. So again, polar is either hydrogen or dipole-dipole. Here's an example of hydrogen bonding. It's kind of this weak attraction with two other hydrogens within the molecule. So not only are they attracted to each other, like right next to their neighbors, but it's kind of this additional attraction. It's kind of weird. And then dipole-dipole occurs in polar molecules. The kind of negative end of one molecule is attracted to the positive end of another, and you kind of get this weird little attraction going. Not quite as strong as hydrogen bonding, but it works well enough. They're both stronger than London dispersion, so it works. All right, let's do the predominant force in these. HCl, that is ionic, because there's a metal, which means the predominant force is an ionic bond. There's a metal, that means this is the strongest is ionic bond. H2S, has a total of 8 electrons. That molecule is polar, because yes, they're the same elements, but we have lone pairs. Polar is either dipole-dipole or hydrogen bonding. I have an H, but I do not have an N, O, or F. So this is dipole, dipole. As with last time, I'm now going to pause. Try and find determine the last two. Give yourself some practice. All right. I'm assuming you've paused and tried the next two. So let's see. H2 is a nonpolar molecule. Here's kind of a trick. Any bond between two nonmetals that are different is polar. But these are the same. So we actually mentioned that phrase earlier. So this is nonpolar, which means London. Lastly, H2O. It is polar, and we do, look at that, we have an H and an O. So this is hydrogen bond. Yay. There you go. That's intermolecular forces. So in terms of strength, our ionic bond is the strongest. Then we have hydrogen bonds, then dipole-dipoles, and then finally London dispersion forces. Here's kind of a few pictures of them. Ionic bonds, again, are the cation and anions together. Covalent bonds represent a shared electrons. And metallic, we didn't really talk about that a whole lot. But hydrogen bond is kind of this weak attraction between hydrogen and something else. Dipole-dipole is basically two different ions. We haven't talked about this one. Haven't talked about that. But London dispersion is between two nonpolar molecules. And you can actually find that the energy to break these is highest with ionic bonds. The next highest is hydrogen bonding that we talk about. Dipole-dipole, London dispersion. And here's a few examples. Alright, we need to figure out which compound in each pair will have the higher melting point. What that means is which one will have the stronger force. Hopefully remember back to melting salt. Stronger forces means higher melting point. So, CS2 is... So we have a total of 16 electrons. So, going to end up having two double bonds. That is nonpolar. And CCl4 is also nonpolar. I know I'm going to have electrons around it. So you're thinking, wait a second, Mr. Booth. They're both nonpolar. What's stronger, nonpolar or nonpolar? Well, I told you about London dispersions, and I said it gets stronger with more electrons. This compound has more total electrons, so this one will be our stronger molecule. Definitely recommend listening to that if you wish. But again, they're both nonpolar. CCl4 has more electrons, so CCl4 is stronger. All right, our next one is HI or KI. HI is a polar bond, dipole-dipole. Ki is, well, ionic. K is a metal. Ionic is the strongest of all of them, so Ki is our strongest. We have ionic and dipole-dipole. So, ionic is stronger. Alright, next one we have Na2O and H2O. Hopefully you actually figured this out beforehand, but I'm actually going to pause real quick. Go try them, try the rest, then I'll go and finish this. Alright, I'm assuming you've paused it. Na2O, well, Na is a metal, so right there that's ionic, that's our highest. H2O, if you work it out, so that's ionic, will get you hydrogen bonding. Ionic is stronger. Na2O is the strongest. So far I've got that and that. Alright, for our last one, CH4. And NH3. I apparently really like these compounds because I keep using them a lot. We have nonpolar, we have polar, which means London dispersion forces for that one. And dipole, oh, actually, no. That is hydrogen bonding for this one. Okay. This one is definitely stronger. So NH3 is the stronger molecule. And that finishes up our video on intermolecular forces and our Unit 3. Congratulations. Woo!